Okay, so this is lecture 2 of computational creativity, and today is a little bit of a divergence from what a lot of the rest of the class is going to be like, because I wanted to talk specifically about, how were computers and technology involved in making art prior to this big deep learning era, right? So you may have heard of GAN art and Deep Dream and things like that, and certainly we all know about DALL-E 2 and Midjourney and so on, right? But lots of people were using technology computers to make art well before these huge deep models. And so today is just kind of like an overview of, well, what did people do? And I want to start out kind of from the very beginning, like in the 1960s, and kind of move up to just before deep learning was a thing, okay? So this is kind of like a historical overview of technology and art, just because, the course is called computational creativity, right? So I wanted to have a little bit of a historical perspective for where did all this stuff come from. Okay, so let's start, 1952, right? So before the digital computer, right, there was the oscilloscope, and there were people who were kind of hacking away at trying to make oscilloscopes make cool looking, temporal diagrams, right? And so this is Ben Leposky, an engineer who became famous for his kind of colorful oscilloscope rendered drawings, kind of like these spirograph things that I had when I was a kid, right? So kind of like these spiral artworks were some of the first things that I could find from like the late or even the early 1950s. Then also not really related to computers, but basically this is a bicycle-powered artwork, right? So the idea is that the visitor to the museum would sit in this bicycle contraption and pedal it, and of course the random variations of how each person pedals it differently is going to create a different kind of artwork, right? So you could argue this is something that is not fully, what's the right word? Non-probabilistic, right? There's a human element to making this art. It's going to be different every time, right? So this artist named Jean Tinguely. This was 1960. Kind of in a similar vein, this is work by an artist named Gordon Pask, and so this is kind of like a network of lights and mirrors and mobiles, and the idea was that the user could interact with this kind of assemblage of hanging stuff in order to kind of put things into position to achieve certain effects. So again, this is kind of like what I would call, injecting the observer into some sort of mechanically produced random art, right? Not just something that you go to a painting and you stare at it and it's stationary on the wall. So there was kind of an upswing when the digital computer became kind of generally a thing that people knew about and available. The word computer graphics wasn't even invented until 1960, right? So kind of like by the late 60s, the idea of a computer had kind of penetrated the popular understanding of what there was. And there was a curator named J.C. Reghart who basically pioneered this big museum exhibition called Cybernetic Serendipity. This was one of the first digital art, shows in the world, in the country, right? And so this was kind of like the first time that all sorts of computer art had been collected together in one place. Very forward-thinking was this artist Lillian Schwartz, one of the first artists to really extensively use computers to create art. And so she worked at Bell Labs, and so that doesn't probably mean a lot to people of your generation, but for like the generation just before mine in academia, Bell Labs was like the holy grail of places to work and kind of do pure research, right? Research that, obviously Bell wanted stuff that would contribute to the way that telephony worked and their phone monopoly. But at the same time, they hired people from all over the spectrum of electrical engineering and physics and math just to do good work. And so one of the people that they hired was this basically artist in residence. And so she was using these very early tools, the light pen, the keyboard and the mouse, right? Which were not a big thing in the 1970s to generate these, computer artworks. So she was a pioneer in this area. Also, these are some early 70s artists, Vera Molnar and Grace Hertlein. So these women learned how to use BASIC and Fortran in order to either create, kind of art directly or to kind of explore random variations, like all these different kinds of squares of different sizes, right? So, people were learning how to create, I guess I would call procedural art, kind of in the mid-70s already. Another example of this is Manfred Moore in the late 70s, who generated these kind of random renderings of cubes in different orientations, right? This is the kind of thing that probably would have been pretty difficult or tedious to do without a computer, that suddenly with a computer became possible to kind of render this series of different kinds of things, right? And another key figure in this kind of world of procedurally generated art in the 70s was an artist named Sol LeWitt. And Sol LeWitt has a particular kind of resonance for me because he was a pioneer in, so let me just say, so Sol LeWitt, if you are in the Northeast, you really cannot miss going to Mass MoCA, which is a museum here in the Northeast that has, I probably should have set up on this page. You're seeing all my Google pictures here. So let's get to May 2012, right? All right, so here we go. This is at Mass MoCA. So Mass MoCA is basically, oh, good, you didn't see it. Excellent. OK, so Mass MoCA is really an incredible environment. It's basically a converted textile and capacitor factory that has these amazing, huge galleries of space. It's like football field-sized galleries. And so they've got one huge building devoted to this artist, Sol LeWitt, who makes these. So Sol LeWitt did not come here and paint these paintings, right? Sol LeWitt left instructions for how these things could be created, right? So it's kind of like an algorithm for creating art. And so he would say, divide the wall into, 10 by 3 squares and paint them in this way, right? And so a lot of the, Mass MoCA exhibit are these huge arrays of colors, but just because there was a recipe doesn't mean that it was entirely procedural, right? Or entirely, non-deterministic, right? Or entirely deterministic, that's what I want to say. Because for example, this thing with these little curled up pieces of paper is something where you might specify saying, okay, for the first panel of this thing, use a ratio of 1/3 white to 1/3 yellow to 1/3 red without specifying exactly where the thing should be. And then on the next panel, you do a quarter red, a quarter blue, a quarter white, a quarter yellow. And so you end up with these kinds of generated artworks that were not really down to the pixel specified. Here's another example of a Sol LeWitt where he basically, I know it's kind of hard to see, let me magnify this a little bit. So he is kind of saying, draw a bunch of points on this wall, and then it's kind of like there's a prescription for where does the next point go. And so Sol LeWitt, would leave these instructions, and then an army of volunteers and other artists would carry them out at different places around the world, right? So again, it's not exactly generative art, but it's also not exactly, it's definitely got an algorithmic element to it, right? So again, anyone we got the long Labor Day weekend coming up, I encourage you to go visit Mass MoCA. It's like an hour away in the beautiful Berkshires of Western Massachusetts. So go check it out. OK, so moving into the 80s, a key figure in the 80s art world was named Harold Cohen. So Harold Cohen wrote a software program called Aaron that was basically arguably one of the first kind of AI tools in making art, right? So this included both procedural and random elements, and he had hooked up plotters with paints and watercolors and so on, so that people who came to the gallery would see this stuff being generated semi-randomly in real time at the gallery. He died not that long ago, but he's one of the pioneers of kind of like computer-generated, computer-mediated art. And then this is all still before you guys were even born, but for me, I remember that in early days of being a professor in the early 2000s, there was this flood of interest in these web-based tools for making art. So Flash was, Macromedia Flash was one of these tools that people would use to make these cool web animations, and artists kind of repurposed it to do similar things. And so Flash, and also there was a tool called processing that artists kind of really took to be able to generate artworks by kind of thinking about it kind of like a block diagram where you could kind of say, okay, I'm going to make an image filter here, and I'm going to add some noise here, and I'm going to plug this into a edge detector here. So it's kind of like this way of hooking together modules to create live web art. So a lot of this stuff was kind of animated or web-based. And to be honest, since Flash is no longer supported anywhere, it may be hard to actually find that artwork today unless it was kind of archived in a way that comes with Flash, right? I haven't seen Flash in a long time. Now, the discussion of using computers to make film is a whole different thing, right? And I don't want to do a whole history of computer-generated film, but really the first time this broke into consciousness was Tron, right? Tron in 1982. Man, when I was a kid, my friend loved Tron. It was his favorite film ever, right? And so Tron has all these really, even to this day, kind of cool-looking animations that were deeply, painstakingly, manually programmed, right? It was not like today where you could just drop this into whatever Unreal Engine and like say make the light cycle go from point A to point B, it took a lot of work to make these animations in Tron. And of course that led to a whole explosion of, now we can kind of trace this lineage all the way through the beginnings of Pixar to the kinds of movies we have today, and even a lot of the visual effects that we see in kind of photorealistic movies are computer generated, right? So this is not about that, right? This is kind of like more on the art side. I also want to talk a little about like computer scientists trying to create art, and that's a topic that is, I'm not an art historian and I'm not an art critic, so this is kind of like fraught with debate about, you can argue whether or not a computer scientist makes something and says, oh, I've made art, right? So we're going to hear actually from Aaron Hertzman, who is like this kind of pioneer in computer-generated art, to talk a little bit about like, what is the relationship between artists and computer scientists. But there was, before I forget, let me just say that this is something that I had to find a place for just because I love the way it looks. This is not painting or sculpture. This is actually Daniel Rosen is an artist who makes these incredible, what they're called mirrors, right? So this is called the wooden mirror. And so it's actually just a series of blonde wood tiles that are all the same, but they're tilted, and the light catches, there's a strong light coming from above to get this kind of range from dark to light. And so when people come in front of this mirror, they see themselves kind of in real time. And he does this with all sorts of different cool, interesting devices, not just wooden tiles, but pieces of metal or pieces of other stuff. So I encourage you to check this out. Just as a reminder, the course website has all sorts of links. If you click down into today's lecture, you can see some links to, some of the stuff we're talking about. And so there's a link on this guy's mirrors. And so he's made all sorts of cool mirrors out of different kinds of pieces of stuff, shiny balls and wooden pegs and woven fabric and so on. So I encourage you to come and check this out because that's pretty cool. So again, I don't know, for me, I just wanted to say something about it because it reminds me of technology and art kind of coming together in an interesting way, right? Because certainly you have to know a lot about servo motors and cameras and stuff like this to make this kind of thing work. And then you could also argue about like whether or not like the Mandelbrot set. So when I was kind of in like middle school, high school, college, this is the kind of thing you'd see on like dorm room walls of the Mandelbrot set. Was so cool, right? Is it art? I mean, can you say someone made it or invented it? I mean, it exists, right? I mean, I guess you can talk about what colors you use to render it, right? But no one actually kind of created this image. It's just a mathematical equation, right? Okay, so let's talk a little bit about computer scientists and art. So a big player in this world is this conference called SIGGRAPH, right? So the ACM Special Interest Group on Computer Graphics, which just celebrated its 50th anniversary, right? So where would that put it? Today is 2023, so that would be 1973, right? And so SIGGRAPH has kind of always had kind of not only technical presentations, but also kind of like this electronic art, exhibit, electronic art theater. And looking back at the archives of those is very interesting. But there were also a lot of computer scientists that were starting to think about, okay, so how can we generate images? For a long time, photorealism was the holy grail, like making things that looked realistic. Like you see lots of examples of, crystal balls and reflecting surfaces and mirrors and stuff like that that are meant to look photoreal. But then people started thinking about, well, what about stuff that is not photoreal, right? So a pioneer in this area was Haberle in 1990, who started to look at, how do I make a kind of a photograph look like it was, sketched, for example. And in this case, what was happening is that he was taking a kind of a source canvas and figuring out ways to lay down lines or strokes in order to kind of render it in a more kind of artistic hatch-based style. And so this is the beginning, I guess, of what you would call non-photorealistic rendering, right? So NPR, non-photorealistic rendering, was a big deal kind of in the late 90s, early 2000s, and I'll be talking about some of that stuff just today. And so, again, that was all kind of pre-deep learning. So what was happening here, more or less, was that, well, let me draw it on a piece of paper. I think that'd be a little bit easier. So what was happening here was that, you'd have an image, and you'd have, an area. Now, again, this is, not everyone here has probably taken image processing, but you guys have all taken calculus, right? So if we have an image, and we look at a point in the image, we can think about where does the gradient point, right? We know that from a calculus perspective, the gradient points in the direction of the greatest increase. And so if I think about black being 0 and white being 1, then the gradient is pointing perpendicular to image edges, right? So this is kind of like saying this is the gradient of this grayscale image, right? And so then if I decide to lay a stroke of paint down, what I could do is I could, click on a point, and then I could draw along the perpendicular to the gradient, right? This is like the perpendicular to the gradient, and I could lay down some color that maybe corresponded to the color of this point, right? And that's probably kind of the way that this kind of sketching was happening, just kind of clicking and drawing. And then of course you can kind of wiggle the fidelity of those color strokes to exactly the colors in the images, or you can let yourself noise that up a little bit to make it seem like, for example, this right-hand image with the geometric solids, clearly there's some noise being added to jitter those strokes to make it look a little more interesting, right? And so, these first algorithms were more, semi-manual in the sense that someone was clicking on these points to draw these strokes, right? Then there was a bunch of follow-on work to try to automate this process, right? To automate the drawing of the strokes. And so one of the seminal works in this area was by Aaron Hertzman. So this was in his PhD thesis in 1998. And the idea was that instead of drawing a lot of strokes that were all the same size and all straight lines, instead you would incrementally build up a painting out of multiple brush strokes that were curved, right? And so then you could kind of say, well, this image now looks like it was kind of like a painted version of a photograph. And this really set off a lot of research in the area, right? So, the cool thing was that by varying the way that you chose to draw these strokes and the parameters that you used, you could take one picture and you could make it look like a watercolor, like this over here. Or you could make it look like kind of an expressionistic style with, long, curvy strokes. Or you could make it look like a pointillist style with a bunch of dots, all using the same algorithm, just varying the parameters. And so let me say a few words about exactly how that works more precisely, right? So this was basically, Hertzman's paper from 1998. The idea was that first I would take the image and I would blur it at a certain scale, right? So we have an image originally, and then I have kind of like the original. I would blur this a little bit. I would blur this some more. So you basically had kind of like this hierarchy, so that by the time you got down to this size, the image is fairly blurry, right? And I start at the lowest blur level, and then what I do is I paint, strokes of radius r onto this image. And so at the lowest blur level, where everything is really broad, my radii of strokes is fairly large, right? So what we do is kind of like we have the current canvas, and we have the blurry image. And we kind of draw a grid on this canvas, and we decide, okay, so we kind of randomly select a point, and we ask ourselves, at this point, what kind of stroke should I draw, right? Similar idea to that other algorithm I showed you, where we kind of look to see, well, if I've got the, suppose I've got like a kind of a image that looks like this. So it's kind of like dark here and, some different color over here. What I may do is I may say, okay, I'm going to start at this point over here, and I'm going to draw some, spline dots, right? So I'm going to kind of follow along the perpendicular to the gradient, laying down control points for a spline along the way. And if I run up against a point where suddenly the color that I'm drawing from the beginning is no longer matching what I'm seeing as I go along the line, like I run up against this new color region, then I stop, right? And then I would fill in a kind of a broad colored stroke over those 4 control points, right? And I kind of just randomly choose points around the image to keep on doing this. And once I'm done with one layer, then I move up to the next finer layer and draw smaller strokes, right? And then I move up to this layer and I draw really skinny, tiny strokes, right? And so in this way, the painting is kind of built up, like I showed over here, from coarse strokes that are kind of like, just like big blobs, to finer strokes, to finally small strokes. And so that was kind of the insight, is that, an artist is going to approach a painting kind of in the same way, right? They're going to start, with big broad strokes and then kind of fill in the details as they go. And so if I wanted to have different styles, I could, I'm sorry, I didn't say this, I'm still getting used to my thing. So again, this is kind of like showing the buildup of coarse to fine, right? And if I wanted to kind of vary the parameters, I could say, so for example, for this expressionistic thing at the upper right, what I want to do is I want to have a higher minimum stroke length to make these strokes long. And I also probably want to have a lower threshold, meaning that I stop the strokes very quickly when the color starts to diverge from the background, right? So the colors are more, what's the right word? Harmonious with the original picture, right? But for a watercolor picture, what I might do is, first of all, I might make the, minimum stroke width a lot bigger, so I kind of have this sense of a wash of color, and I might make my fidelity to the underlying canvas a lot less, so I'm allowed to kind of have this more kind of dreamy looking feel. And then also you can see there's some jittering of color, right? So here I'm introducing some, pink colors over here in the lower left-hand image that don't really exist in the original image, probably because I've added some color noise to make this kind of, again, a different effect. And so it was very cool that you could let this algorithm just kind of do its own thing and create these painterly rendered strokes. And then there was a whole flurry of excitement based on that paper, right? So then people started thinking about, okay, how can we make this better? So for example, one of the extensions of this paper was to try to, this was what we would call a greedy algorithm originally, right? Where you're just kind of putting down these strokes randomly, well, I guess I wouldn't call it a greedy algorithm. It was more like a random algorithm where you're just kind of laying down strokes. If you ran the algorithm again, the strokes would start in a different place. So there wasn't a lot of coherence. There also was no guarantee that the strokes that you put down would somehow be the best strokes in any sense, right? So then there was talk about, well, how could we choose at every level, the globally optimal set of strokes? So then the picture will look a little more faithful to the original, right? So here you can kind of see that the left-hand picture is one in which the strokes are kind of laid down locally, and the right-hand picture is one in which the strokes are kind of globally optimized, so the fit is a little better. If you look at the image edges, it looks a little more faithful. And then there was a lot of follow-on work of just making the strokes look kind of qualitatively different. You can kind of apply different strokes in different areas. And then, of course, can you make this kind of work on video, right? So here's kind of an example where first of all, can you make it work fast? So this is a rendered video, but there were versions of this that were kind of like a painted mirror where you'd go up to this thing and it would do this, it would make these kind of painted versions of you in real time. It was pretty cool to see. This, again, is a music video that's been kind of painted over, and the style is subtly changing, between scenes. Again, I don't remember exactly what version of the algorithm this was, but there may not have been a lot of temporal coherence between the strokes in this situation, right? So for example, there's a lot of jitter in the background where that could have been intentional, but also it's not like necessarily the strokes are really sticking to the people very well. And then here's some follow-on work where there's a lot more attempt to make sure that the paint strokes are really sticking to the object, right? So that as the person moves around, it seems like the paint is stuck to the person in a realistic way, right? And of course, you could make a more non-photorealistic version of this that's really kind of out there, and you can see that these kind of rice grains are kind of following along with the contours of the person as they move around over time, right? So again, this kind of refinement, we started off in 1998 on the basic idea, and this is work that's done in 2012 to kind of make things better. And of course, things like global optimality and so on generally take a lot of computational power, and so this kind of goes hand in hand with computers getting better and better. And again, if any of you know about computer vision topics like optical flow, this is kind of you can imagine that you kind of want to estimate the flow field between image 1 and image 2 to make the strokes kind of stick to objects, right? And also, if any of you know anything about visual effects, this is related to kind of what's called rotoscoping, which means how do you get contours that someone has manually drawn to kind of follow forward in video without having to manually draw the contours every time, right? Okay. So let me stop for a second and ask any questions or comments so far about what I'm talking about. Okay. So another milestone in kind of image stylization was another paper. Well, before I forget, so this is kind of like a kind of Hollywood version of this. So this is from a 1998 movie called What Dreams May Come, a Robin Williams movie. And the premise of this scene in particular is that this guy's wife was an artist, and he goes into one of her paintings, and it's kind of like this dreamlike thing where suddenly, it's this kind of he's real, but everything else is like he's in the painting. And so to make it seem like these paint strokes were, slipping around realistically like oil paintings, this was kind of like, again, some combination of starting from a SIGGRAPH paper and then kind of a lot of visual effects artists working hard to make it look better, right? Because a lot of times what is working at a technical demo level for a conference like SIGGRAPH is not ready for rendering at 40 feet wide on a movie screen, right? So there's an interesting relationship between graphics and vision research and kind of production that you'd find in the movies. And so for that, you could take my other class on visual effects. Okay, so another key paper in this area of non-photorealistic rendering was called Image Analogies, again by Aaron Hertzman and his colleagues in 2001, okay? And so the premise and the idea was very simple, right? So just like when you take it used to be, at least when I took the SAT or the GRE, they had these kind of like analogy problems, like, elephant is to big as mouse is to blank, right? You select small out of the categories, right? So the idea would be that you show the algorithm an example of, okay, here's my source image, and here's what it looks like in some stylized way, and now I give you another source image, what should that image look like, right? So A is to A prime as B is to B prime, right? So the idea would be that A and A prime are kind of given to the algorithm as examples of how do I want to stylize an image, make it look like this, and then B is a photograph that I turn into B prime, which is like a painted version, right? And so this again was a landmark in this kind of rendering, because suddenly you could take like an image on the left and make the image on the right, which has these kind of very appealing, like big brush strokey looking things that kind of look like it was painted with oil paint, right? And then you could provide it with a different example where it's like, okay, I want it to look like this image on the right, and then you can take an original image here and turn it into this kind of thing that looks like it's got thick, chunky, painted brush strokes, right? It was suddenly very cool, right? To be able to kind of like just press a button and make it come out like this, right? Now, one thing you may have noticed is that, so if I want to make it look like, I'm not sure if this is Van Gogh or not, maybe this is not, but something like this, usually what you would do in this algorithm would you'd already have the painting that you want to make it look like, right? But you don't have like the equivalent of a photograph of that scene, right? You don't have the version of this painting without, the paint strokes, right? So there was a kind of a clever way of saying, well, first what you should do is you should take the painting and blur it out in such a way that you remove all the identifying kind of texture and paint strokes that make it stylized. So, and it was kind of the same thing for this example, right? So A prime is actually the painting that you had access to, and A in this case was something where they took the image and they blurred it in such a way that the edges were preserved, but the paint stroke texture was removed, right? So that's what you would do if you didn't actually have A and A prime together. And so, again, this Image Analogies paper produced some very striking images, and even worked on things that looked like kind of hand sketches and so on. So for example, here, the A prime is this kind of hatch sketchwork in the corner. This is blurred to produce the kind of source image A, and then I could take some black and white photograph and make it look like it was sketched, right? Now, of course, there's lots of details to how to make this work in general for these various algorithms, but the wide range of results that you could get with this Image Analogies paper were, again, very striking, right? So you could kind of make these cool textured looking things. And again, for those of you that grew up in the world of Instagram filters, you can kind of get a sense that this is the history of where that kind of thing came from, right? And so let me say a little bit about exactly how this Image Analogies paper worked, right? So this was Hertzman and colleagues in 2001, and the paper is called Image Analogies. So the Image Analogies paper, again, the idea would be that I have A is to A prime, and this kind of notation with the double colons, I don't know if they still use this on the SATs and GREs, but the kind of idea was this is like the source. This is like the stylized source. This is the target. And the goal is to learn from this relationship in order to produce this B prime. The goal is the stylized target. And so the cool innovation of this was, if you look back at the previous work with the strokes, you had to really carefully program the style by means of minimum and maximum stroke lengths and fidelity to the underlying image and stuff like that. This is more like, make it look like this, right? No need to actually kind of specify how to make that happen. The algorithm figures it out, right? So this was kind of like, kind of painting by example, right? Which was a cool idea. And so, again, let me just write down what I said. So, in practice, if A prime is a painting, what I do is I create A by kind of some sort of edge-preserving blur. So you're kind of making a blurry version of the painting. And so the basic idea for how you do this is that you do what's called a Gaussian pyramid. So again, I realized that image processing was not a prerequisite for this class, but I can kind of hand-wave my way through what this is. So the idea is that what I'm going to do is I'm going to start doing this with a very small image. So I'm basically going to resample these images until they're very small. I'm going to make a very small version of B prime, and then I'm going to start to build my way up to a big version of B prime. Okay? So the idea is something like this. So what we do is build what's called a Gaussian pyramid. Which is a fancy word for small, blurry versions. So I have kind of like my, this is my original A. This is my original A prime. This is my original B. And I make something that's basically half as big and a little bit blurrier, and half as big and a little blurrier, and so on, right? So I can do this for all these images because I have access to all of them. And what I'm trying to do is I'm trying to build B prime. And so what I do is I kind of start at the lowest level, and kind of what I'm doing is I'm saying, okay, we kind of do this in a recursive way. So let's imagine that I'm looking at somewhere in the middle of the stack after I've already done a little bit of rendering. What I could do is I could say, okay, I'm going to look at, this is like A at level L minus 1. This is A prime at level L minus 1. This is the bigger version of A at level L. And this is the bigger version of A prime at level L. And I have the same thing for B, right? I have the smaller version of B. And I have the smaller version of B prime. I have the big version of B at level L. And now what I'm going to do is I'm going to figure out how do I create this B prime at level L, right? So what I'm going to do is I'm going to say, okay, imagine that there's some sort of, structures in this image, right? So let's suppose that I've got, some sort of like an object that is kind of like sticking out like this. And this is kind of like the bigger version of it. So I've already generated, and again, maybe I've got some sort of different size thing over here, right? So I'm not making exactly the same thing. Now what I'm going to do is I'm going to say, okay, let's suppose that I've already built up the image up to a certain point, and now I'm kind of trying to say, okay, I built this up, and I want to know what should I be doing at this point, right? What I want to do is I want to build a little neighborhood around this point, and I want to kind of say, okay, I know where this is in all of my images. What I'm going to try to do is I'm going to try to find the closest thing in the source image that looks kind of like that, right? So I've got a little nose sticking out on the right-hand side. What I'm going to do is I'm going to try to search for a place that has good agreement at all these scales, right? So it might be like saying, okay, I want to find like a little promontory like this. You have a cost function that tries to make, these matches all agree as much as they can. So you have a cost function that basically says, at these multiple scales, try to make all this stuff match as well as you can, right? And then, once you've done that, you can say, well, now I can take this best match in the stylized A prime, and I can kind of like take the part that I don't have, which is this region, and I can kind of cut it and paste it into this region, right? So it's kind of like a patch-based algorithm where I'm finding pieces of the stylized A prime to kind of stick into places into B prime. And the best match kind of depends on this multi-scale idea. Now, there's also kind of like, to be totally complete, there's also kind of like a what's called a smoothness prior. And what that means is that I don't necessarily let myself just take A prime patches from all over the image. Instead, what I do is I kind of have a little flag that says, well, I don't want to, have the, constructed B be made out of stuff from all over A prime. Instead, I want to kind of pick patches that are neighbors in A prime to create B prime, right? So it's kind of like some little extra term that says, yes, try to find the best match, but don't stray too far away from where you took your last match, right? So it's like saying, well, if I knew that I generated this stuff over here based on, this area, well, then maybe I should be adding a little weight that says I should put some extra consideration on the next neighbor to where I was before, right? So the idea is to say, yes, get the best match, but also have a kind of a weight term that makes the whole image coherent and smooth, right? That's the way that you can obtain stuff like this, where it seems like there are these kind of long continuous paint strokes because somewhere in the A prime, there were these, kind of things, right? So there's kind of like going to be a trade-off between color fidelity and neighborness in the image. Again, for more details, you can read the original paper. And if you look at the, again, the website for today's lecture, you can see that, you can download the original image analogies paper and take a look at it, right? And so if you want all the details, you can find it there, right? These days, probably you can find a library that will do it automatically almost, right? Okay, so again, this image analogies paper was hugely influential because of all the stuff it could do, right? So not only could it do this kind of, show me, make it look like this kind of thing, but also it enabled this kind of paint by numbers idea, which was really cool. So the idea being that you could take a photograph or a source image, and then you could kind of outline, okay, so I'm going to manually annotate, this is river, and this is forest, and this is grassland. And then I can kind of paint on the bottom a new image with those kind of red, green, blue colors. And then I could synthesize a photograph looking thing that had the river and the mountains and the forest in the same places, right? So I think that's a pretty cool idea of kind of like being able to, remix these elements of the original image in this, fairly photorealistic way. Of course, it doesn't have to be photorealistic. You could also do this with a painting or something else, right? So that was pretty cool. All right, any questions or comments about this kind of thing? Okay. So let me talk about a little bit other related work that kind of goes along this line. So again, these are just kind of like some greatest hits of stuff that kind of happened in the 2002-2010 timeframe, right? So this was a stylization paper that kind of used a combination of image segmentation, like automatic color segmentation, and gaze tracking, like where do people look at an image when they look at artwork, to kind of render an image in such a way that, for example, where the user is looking gets kind of like higher detailed strokes, and where they're not looking gets kind of like broader strokes. So the idea would be that you'd use this kind of human-guided salience map to understand how you should lay down strokes in the image, right? So that was one of those pioneering papers. If you have a 3D model of what you're trying to draw, right, there was some very interesting work by Winkelbach and Salison in the mid-90s where you could basically render a 3D model as if it looked like a sketch, right? So you had to kind of specify the 3D model, a light direction, and then you could kind of create these kind of, again, artistic looking renderings that are actually just like kind of cold, hard CAD models underneath, but rendered in an interesting way, right? And so again, there are lots of interesting stylistic choices to make about like, well, some of these bricks over here, for example, are hatched in and some of them aren't, and they're hatched in different directions in different ways. To be honest, I don't remember the details of like how this stuff is done and how manual it is. You can make kind of like stippling effects and hatching effects in the same thing. You can make the hatch marks kind of move along the contours of things. So again, this was pretty cool when it came out. This is work that I've always liked also, right? So this is kind of like, how do you make a photograph into a tile mosaic, where the only options that you're given are basically squares or rectangles of solid color. And you can think about that like an optimization problem, right? So if I only give you, a tub full of tiles of fixed colors, how can I arrange them together in such a way that looks as much as possible like some original image? And again, you can imagine there's some sort of a constraint that says you want there to be as little kind of grout between the tiles as possible, right? Otherwise, you'd have like a big kind of, empty mess, right? So here, the right hand or the left hand side is basically squares that are a fixed size, and the right hand picture is squares that are allowed to change size. And of course, you can imagine that if I was allowed to make squares of infinitely small size, I'd basically get the original image back again. So there has to be some constraint that you can't get the squares too small, and also you kind of want the squares to be as large as possible to make sense, right? So regions of the image like the sky that are kind of broad and flat colored, I use big squares, and in places where things are changing rapidly, like the windows and the people on the porch, I use small squares, right? So I always thought this was kind of like very pleasing looking work. And then there was kind of follow-on work on this tiling idea to basically the user. This is again similar to like a paint by numbers idea, right? Where the user supplies kind of a sketch of, I want these areas to be white, this area to be black, and so on. Or maybe it was just a segmentation of the images by region, and then it would figure out the right colors. But instead of using, solid colored tiles, it was using a library of kind of like pictures of things to make this kind of like photo mosaic, right? So suddenly you could make this thing that when you get up close to it, you see the tiles are actually like little images themselves, right? This kind of thing was a big deal back, again, 20 years ago. You'd get these, they did call them photo mosaics, right? You'd kind of like see a poster and it would be made up of like pictures of your family, but you pull back and it's a picture of your Grand Canyon vacation, right? So how to automatically make these kinds of tiled photo mosaics was cool. And this was interesting because the tiles are not rectangular. So there was a little bit of interesting optimization problem there. This was famous work back in the late 90s also, this kind of like Seussification filter that you could apply. So again, you start with a 3D model of terrain and trees and stuff like that, and then you could render it in such a way that looked like it was a Dr. Seuss diagram, right? So going from the left to the right was actually fully, as I recall, fully automatic, right? And so again, this is a great example of totally non-photorealistic rendering, right? Going from a stick diagram to this Seuss filter. That was pretty cool. And then there was a whole range of kind of like what I would call toon shading type of papers that came out kind of in the late 2000s. A lot of them came out of this group by Kang et al. And so again, you can see the predecessors here to probably a lot of the kind of goofy Instagram filters that you grew up with, right? So how do you take a photograph and then kind of like stylize the edges? And again, this is not exactly painterly rendering in the same way, but certainly you could kind of view this lion as having been painted with a series of digital brushstrokes, right? It looks a lot different than the Hertzman version, but it is something that is based, in some sense it's based more on kind of like fundamental image processing techniques that is on kind of like computer graphics techniques. So again, this is like the beginnings of those kinds of tools. And then, again, in the mid-2000s, there was also this kind of interest, if we go back to how this is impacted into film. So there was a movie called A Scanner Darkly, which was an entirely rendered version of live action footage in this kind of toon-shaded style, right? I've only, to be honest, ever seen clips of this movie because it seems like it would be really fatiguing to watch this movie in real life. But I mean, this is kind of like the predecessor of all the, Spider-Verse movies and the movie, the Teenage Mutant Ninja Turtles movie that just came out that looks kind of like stylized. All this stuff is kind of like the forebears of where these, more modern movies came from, right? And this, again, was extremely laborious. Took teams and teams of artists and animators to make the colored pieces stick to the people's faces and so on, right? So again, I think it's very interesting to kind of look back at the history of this stuff. This takes us to around 2010, which is kind of right before deep learning and so on became viable and possible, right? So, these old methods are generally what I would call procedural, meaning that there's an algorithmic recipe that you can look at in a SIGGRAPH paper, and you can understand that if I tune this parameter, it will have this result on the resulting artistic image, right? It wasn't hard for a user to figure out how to tweak the parameters to get different artistic effects, right? And so it's not really that way with the kinds of deep learning mediated algorithms that we'll talk about in future lectures, right? So for example, one of the things we're going to talk about in a while is kind of this famous deep dream algorithm, right? So deep dream, is the thing that people use to make these crazy, neural net-based, renditions of photographs where they kind of hallucinate crazy shapes and crazy faces and dogs and stuff like that inside images, right? So here, it's a lot less control for the user to be able to make an image that is exactly what they want, because the network has millions of parameters to tune, right? In a similar way, kind of skipping forward to what we're going to talk about in a few lectures. Let me see if this will work. I don't want to mess up my streaming pipeline, but it's possible that I could mess it up. So I mentioned in the previous class that we're going to be talking about GAN artists. And so let me just, go to my OBS for a second here. I want to get the right slideshow. Here we go. Or maybe my OBS is messed up. I'm sorry. Go back to my notes. So in the interest of not messing up my recording, let me just say that, up to now, up to approximately 2010, kind of computer art would be what I would call fairly, algorithmic with a few kind of natural parameters. And then kind of the deep learning age, we kind of have billions of parameters. So it's still something that you can use to make interesting stuff, but the quest for kind of making it easy to control is a lot harder. And so, for me, I think that these old school 90s algorithms still have a very charming old school look to them, right? I find that the results that you can obtain with those algorithms is, to me, still as appealing or more appealing than some of the stuff that you can make later, right? So for example, we're going to talk extensively in the same lecture we talk about deep dream, we're going to talk about what's called neural style transfer. And so, just show you an example of that. So neural style transfer is basically, similar to the original image analogies paper, where you kind of say, make it look like that. Make my dog look like Kandinsky, right? And so, this is in the same vein as image analogies, right? Where you supply a Kandinsky and you supply a picture of your dog, but it's done using this deep neural network, right? For me, I think that, yes, it's cool to look at, but I still find the old stuff to be a little more kind of, endearing in a way. But we will talk about this stuff too once we talk a little bit more about, neural networks and so on. Okay, so let me stop and ask. Any questions or comments about anything I've said so far? So like I said, this is a fairly orthogonal lecture to the rest of the class, but I think it is kind of interesting. And again, you may take some inspiration for when you're talking about what you might want to handle for your projects. Don't forget that there was a whole lot of stuff before Midjourney and DALL-E, right? And in some sense, this stuff is more kind of humble and controllable than that stuff. So I wouldn't take it amiss if you decided to look back into some of this older literature and try to incorporate some element of it or be inspired by it for your work. Also, while we're talking about it, a lot of this original work came out of SIGGRAPH. And so since this is the 50th anniversary of SIGGRAPH, there is actually quite a bit of cool stuff. So if you're interested in the history of computer graphics, there's a great article that is more or less a long reminiscence of people who were there from the very beginning. Basically, it's like a long oral interview of SIGGRAPH from the very beginning of humble conference in Boulder to these massive conferences that are now in LA. And so, of course, not all SIGGRAPH is much more than just this non-photorealistic rendering, but it is something to see, and I think that it's worth taking a look at. In the same way, ACM released a compendium of like the best SIGGRAPH papers for the past 50 years. This is like volume 2 of that. And so, let's load it again. Don't know why it's not liking me. Oh, here we go. So if you're interested in reading some of these stuff that I was mentioning, in the non-photorealistic rendering section of this free thing, you can find basically like the original pen and ink illustration. The image analogies paper is in here somewhere. Lithograph. Yeah, here it is, right? So again, I mean, for RPI students, you can find all this stuff in the ACM Digital Library anyway, but even if you don't have an ACM subscription, most of this stuff is available. So I encourage you to check it out. And again, like I said, the stuff that I think is most relevant is on my course website for this class. So like you can see in lecture 2, there's the original Hertzman papers. There's a paper that is more or less like a kind of survey paper on kind of, up to 2013, all the different kinds of algorithms for image stylization. That's worth a look. And then there are a couple of interesting articles on kind of like, the genesis of generative art. So this article by Jason Bailey in Art in America kind of goes off from the very beginning of some of the stuff we talked about. We talked about like Grace Hertline and so on, all the way up to kind of the age of Flash and then the age of GANs, right? So, this is a great survey paper. And then interviews with these computer art pioneers. This is a, interview with Vera Molnar, who is one of those 1970s generative artists that we talked about. It's interesting to talk about, they're interviewing her and, she's like, what does generative mean to you? I don't know what it means, right? It's like, this is a whole different world of how people grew up thinking about art. And then this is the obituary of Harold Cohen, who died not that long ago. This is from 2016, right? And kind of telling the story of his life and his artwork, right? So, so I do encourage you to kind of click on these things and follow on. The last one I put in here is the Lillian Schwartz, the woman who is basically the artist in residence at Bell Labs. So again, part of what I want to get, kind of what I want to encourage in this course is kind of like this slightly broader perspective on, how these computer graphics and machine learning algorithms integrate into, the art world, right? And we'll definitely talk a lot, especially when we get to the GAN artist part, about like, as it becomes easier for the average person to manipulate these, kind of like publicly available source code, who is the artist there? Who is responsible for the creation of this artifact? It's kind of interesting stuff to think about philosophically. Okay. Pause for comment. All right. So I think what I'm going to do is I'm going to stop the recording. So for those of you watching on YouTube, I'll see you next time.